Hey guys, BuildZoid here, and today we're going to be doing another Z790 transient response video. Today we're going to be testing the MSI Z790i Edge Wi-Fi, so the ITX motherboard from MSI. I bought this board. It's not a review sample from MSI. You might be wondering why I didn't request a review sample, and the reasoning for that is very simple. In the past, if MSI sampled me an ITX motherboard, it was always on loan, and it was always on loan for a much shorter period of time than I wanted it for. So yeah, I decided to buy this one, because I don't really feel like sending the motherboard back after a month or two. Because, yeah, that's how it's gone in the past, and I want the board for longer than that. Also, I really wanted a ITX board to use with, like, high-end 13th gen CPUs, because if you're mounting some questionable cooling systems to GPUs, ITX boards have the wonderful advantage of the PCIe slot being right on the edge of the motherboard PCB, so if you have, like, a heatsink that overhangs the GPU PCB downwards, you don't need to use like a bunch of PCIe risers to get it to fit. So, yeah, I wanted a ITX board that would just be mine for that reason. So I did buy this board. And so thank you for thank you to the channel supporters for making this purchase possible. The CPU we're using here is a 13900K, which was provided by Intel, and then I have some Hynix ADI memory sticks installed in the system. Anyway, for the settings that we're running here, we're just running 5.2 on the P cores, 4.2 on the E cores, and 45 on the ring. 4.5 on the ring. This is just like a very basic, like this is not actually an overclock, this is an underclock. The thing is, I don't really feel like dealing with the CPU crashing when we're intentionally running the motherboard with like really suboptimal LLC settings. So we have the CPU frequency pretty low so that it doesn't crash. Anyway, let's talk about the actual LLC settings. Now, this board has 8 different LLC modes, but funnily enough, there's only really like 5 different settings here because modes 1, 2... So the thing is, basically, the difference in VDROOP between mode 1 and 2 is 10 millivolts. The difference between 2 and 3 is also 10 millivolts. And this is with a 13900K. And the 13900K pulls a lot of current, and the way the VDROOP works is that it's proportional to the amount of current that the CPU is pulling. So if a chip that pulls north of 200 amps sees a 10 millivolt difference between mode 1 and 2, that means on like a 13700K or a 13600K, mode 1 and 2 would have even less of a difference in terms of VDROOP. Which really makes you question why the hell does mode 1 and 2, like, why is there a mode 2? But anyway, yeah, so 10 millivolt VDROOP, another 10 millivolts more VDROOP, another 10 millivolts, another 10 millivolts, and so it's like from mode 1 to mode 5, there's a difference of 40 millivolts VDROOP with a 13900K. Which basically means at mode 1, with 1.18 volts, you get the same load voltage as mode 5 with 1.22 volts. So basically, mode 4, 3, and 2 are completely useless, because they're like... there is not very much difference between mode 1 and 5, so I don't know why there's also 2, 3, and 4. Like, these may as well not exist as far as I'm concerned, because they're basically the same as mode either 1 or mode 5, depending on which direction you look at it from. And they all suck in terms of voltage regulation, because, like, you know, this is literally, like, this is no VDROOP whatsoever. Then we have, VDROOP, like a negligible amount of VDROOP with a negligible improvement in terms of voltage regulation. Imagine that. And then by mode 5, we actually get something where it's like, okay, we're actually starting to see some somewhat significant VDROOP, but it's still just 40 millivolts, and the voltage regulation is still pretty terrible, as we shall see. Then you get to mode 6, which is a 80 millivolt VDROOP increase from mode 5. So, yeah, the way these are set up is just kind of wacky, because, yeah. And then from mode 6 to 7, that's another 80 millivolts, and mode 7 to 8, that's another 80 millivolts increase in VDROOP, so basically, you have a 10 millivolt difference, 10 millivolt difference, 10 millivolt difference, 10 millivolt difference, 80 millivolt difference, 80, 80. And this is with a 13900K. If you have a lower current draw CPU, the differences between the different LLC modes will be smaller because VDroop is proportional to the current draw of the CPU. Anyway, so yeah, I have no idea why modes 2, 3, 4 even exist on this board, but I guess, well, they're there. We're not going to be, like, I'm not going to bother showing them today on video because they're the same as, like, mode 1. Like, mode 2 and mode 1 are interchangeable as far as I'm concerned, and mode 3 and 2 are also basically interchangeable. Like, you get the idea. There's just not a significant difference between them, so we're not going to bother testing them. We're just going to test one. We're going to test 1, 5, 6, 7, 8. Anyway, we do have this rather interesting setting, which is called load line saturation control. Basically, it allows you to, like, delay the starting point of the VDroop, or it's not really delay, but, like, offset the starting point of the VDroop. So it allows you to shave off some idle voltage. I'm not really sure, like, I don't see that as, like, super useful. Yeah, like, I don't really see much utility in the ability to do that, but it doesn't hurt anything by existing, and it's so it's kind of neat. Yeah, I guess I'll show you how that works. Then you have overvoltage protection, which we have maxed out for testing, overcurrent protection, which we have maxed out for testing, and switching frequency set to 500 kilohertz. I've not bothered to check if higher switching frequencies make any difference in voltage regulation. I imagine, like most modern motherboards, raising the switching frequency either does nothing or actually makes the voltage regulation worse. There's quite a few examples of that out there, including some motherboards having incredibly glitchy load line behavior when you totally, like, go into the very high switching frequencies. So that's one thing. And the other thing is this is an ITX board that struggles with VRM cooling because there's just not enough space for a proper heatsink for the VRM. Like, it's a very nice VRM using, you know, top-of-the-line parts. They squeezed about as many phases onto the board as you can, but that doesn't change the fact that, like, you just can't really have that big a heatsink, and the 13900K is a very, very thirsty CPU. So, yeah, raising the switching frequency to get negligible improvements in terms of voltage regulation at the cost of significantly increased VRM heat output on an ITX board where the VRM already runs quite hot just doesn't seem like a particularly good idea. So we're not going to be doing that. Anyway, so yeah, and we're going to start off with override mode and just 1.18 volts and mode 1 LLC. And so that's that. Let's take a look at how the board does in terms of voltage regulation. Now, I guess I should explain what we're well, I guess if you're new to these videos, I should explain what we're looking at. So basically, the goal of this testing is that we want to see as small a difference between this measurement right here, which is the average voltage, and the absolute minimum voltage. And the reason we want a small difference between these two is because if the CPU isn't getting enough voltage to run at the frequency that it's trying to run at, it will crash. And this voltage right here basically controls the CPU's power consumption. So the more average voltage you need, like the more average voltage you have, the more power consumption the CPU will have. And the lower your minimum voltage is, the less stable the CPU is. So basically we want our average, like in a perfect world, average voltage and minimum voltage would be the exact same thing. Unfortunately, due to physics and imperfect real-world components, actually mostly due to the imperfect real-world components, your minimum voltage will never be the same as your average voltage, but you know, if you have the load line calibration set correctly, you can get pretty close, especially if the motherboard is also well designed. So anyway, yeah, that's what we're aiming for. For the workload, we're going to be running Y-Cruncher small FFTs. Also, if you're wondering what's up with this like spike that we're seeing right now already on the oscilloscope, Windows basically has a event timer, which it uses to check that everything is running correctly. Every time that event timer basically kicks in and Windows checks that everything is running, we see a bit of a voltage dip because basically when like it spikes CPU usage for like a fraction of a well, yes, a fraction of a millisecond, but like it's the event we're seeing here is in the range of like 50 microseconds right now, right? Like if you look at the oscilloscope over there, that's like, yeah. So these kinds of voltage like the reason we need an oscilloscope for this is no monitoring software is ever going to pick up voltage deviations that are in the range of microseconds. So anyway, we're going to zoom back out of that to like 10 milliseconds per division. Also, if you see, like, moving the mouse obviously increases CPU usage because the operating system is like, oh, what's he going to click on? And what I'm going to click on is Y-Cruncher. And so now we have Y-Cruncher running. Now, if I don't touch the mouse, we do have some undershoot, but it's not too bad because we still have the Windows event timer basically checking that everything is still running. And so every time the event timer does its thing, it basically... What's basically going on is we have Y-Cruncher running at a relatively constant amount of current draw because this is a 50 megabyte data set, so it fits almost entirely into the L3 cache of the CPU, and so there's no like memory access related processing stalls, and so the current draw is relatively constant. But then Windows comes along, interrupts Y-Cruncher with the event timer, so we see a current draw, like we see the current draw basically reduce from the CPU side, which causes a voltage spike because there's a whole bunch of energy stored up in the output inductors of the. Actually, like, just the inductors of the VRM. I don't know why I'm saying output inductors. It's not like... Well, technically, you have, like, an input filtering inductor, but you wouldn't really consider that part of the VRM. So, anyway, yeah, so the inductors of the VRM will have a bunch of energy stored up in them. And when the current draw suddenly changes, that energy suddenly has nowhere to go, and so it leads into this voltage spike, which is suppressed by the capacitors that are on the motherboard to basically deal with this kind of thing. So we have a sort of like what we're seeing here is excess energy from the inductors being dumped into the capacitors, which drives up the output voltage of the VRM. And then the VRM, you know, reacts and we see the voltage come down a bit, and then it undershoots a bit because Y-Cruncher starts running again, and so the current draw very quickly ramps back up. And so we see a little bit of voltage undershoot there. However, this is if we just, you know, let Y-Cruncher run on its own with nothing really happening. If we zoom out a bit, I could put the... Yeah, we're going to zoom out a bit. If I move the mouse, things get a lot worse. So I'm just going to quickly clear the statistics, also move the trigger out of the way, and we're just going to move the mouse around a bit. And yeah, we're seeing, you know, minimum voltages that are, like, way down. Like, we're going below our idle voltage, which is really, really bad, right? So, yeah, this is not great, which is not really that surprising. So I'm just going to end Y-Cruncher here. And basically what we're seeing is that our average voltage while running Y-Cruncher was about 1.227 volts. And the minimums, when you'd move the mouse around, are like 1.13 volts, which just, that's what, like 110 millivolts of undershoot. So that is very bad. What's especially bad about this is literally worse than our idle voltage, right? If I reset our statistics right now, our idle voltage, average idle voltage, is 1.18 volts. And our minimums at idle are 1.14 volts. Like, this isn't, you know, like, the thing is the oscilloscope is hooked up to the back of the motherboard, so we're not seeing the, like, full extent of the undershoot at the like, silicon itself. And we're also seeing, like, the reason why the voltage goes up when Y-Cruncher, like, the average voltage goes up when Y-Cruncher starts is because there is a voltage drop across the CPU socket itself. So the voltage regulator on the motherboard is regulating against the CPU silicon, whereas we're measuring on the motherboard, like, on the back of the motherboard, so, you know, we see more average voltage than the CPU is actually receiving because a lot of voltage is just kind of lost across the socket itself. So the thing is, yeah, like, Mode 1 LLC is just terrible for voltage regulation. That's really not surprising. There's no V-droop. We're literally seeing undershoot, underload that is worse than what we get at idle, both in terms of idle average voltage and undershoot at idle. So, yeah, Mode 1 is unusable, which is really unsurprising. Oh, I guess one neat feature that I could want to point out about this board, since we're doing this video right now, is that this board in hardware info does have the DyeSense voltage reading accessible. Right, so we have this voltage reading right here. This is VR Vout, and that is a core voltage reading directly from the voltage regulator on the board. So you can see that's spot on 1.18 volts right now. And actually, if we run Y-Cruncher again, and this time I'm going to do it like this. Where is VR Vout? You can see that our VR Vout doesn't change. Sure, our core voltage reading on the motherboard itself is now 1.27 volts, 1.2 volts, and here we have 1.18. But this, I actually don't know where this is from. The Super I/O normal, like basically, it's not a DyeSense voltage reading. So this is the voltage that the CPU itself is seeing. I'm not sure where this is measured from on the motherboard. MSI has done some weird things with their like Super I/O voltage readings in the past. Yeah, actually our average voltage right now, even on the oscilloscope, wait, no, that's just because of the average, there. Just because of the averaging of the idle voltage, but yeah. I'm not sure where this reading is from, but this is what the actual CPU itself is seeing, this voltage right here. Anyway, so in mode 1, we don't have any V-droop. The voltage isn't going up or anything. That's just the CPU socket impedance getting in the way. Which is also part of why, you know, voltage regulation is so hard. It's just because you have, like, motherboard power plane impedance, CPU socket impedance, that kind of thing. So anyway, now we're going to restart. And the reason I pointed out the VR Vout sensor on the board is because on some motherboards that sensor is inaccessible, which is kind of annoying. If you're trying to judge if an LLC setting is like overly aggressive or not, because you just don't know how accurate the onboard voltage sensor is. Like on some motherboards, it's really bad where they're going to be reading like because like the various motherboards will have like different amounts of voltage drop across the CPU socket, and then where the Super I/O, which is like the usual core voltage sensor that you see in like CPU Z or the Vcore sensor that you have in our hardware info, like the Super I/O is normally hooked to some kind of random location somewhere on this Vcore power plane. So on some motherboards it reads like really high or kind of close, or it's all over the place. So having a motherboard with this VR Vout sensor is actually really convenient if you're trying to judge how much V-droop the LLC setting actually has, because on most motherboards, on the vast majority of motherboards, the Super I/O voltage reading is just unreliable. And there's really no way to know how unreliable it is without like extensive extra testing that is annoying to do. There are some high-end motherboards that have a circuit to like replicate the DyeSense reading over to the Super I/O, but when I say high-end motherboards, I mean boards north of $500. You don't really see that functionality on anything else. Anyway, so next we're going to go to 1.22 volts and mode 5 LLC. Which is still going to have terrible voltage regulation, but it's going to be significantly less terrible than what we just saw. What was it, like 110 millivolts of undershoot, which is unusable. Yeah, that's kind of the nicest thing I can say about it. Like, you do not want to have 110 millivolts of undershoot. There's just, yeah. That's just bad. Especially when you're measuring it from the back of the motherboard, where we're not even seeing the full extent of it. I'm not sure how much of it gets hidden by the impedance of the CPU socket, but certainly we are not seeing all of it. Anyway, so now we're idling at 1.22 volt, well, almost 1.22 volts. And if I start Y-Cruncher, and you can already see that our like minimums have gotten a little bit better, but then that's mostly because our idle average voltage is somewhat higher. But now we're going to start Y-Cruncher, and our average voltage goes, yeah, I tried my best to match all of the voltages, but instead of getting the 1.227-ish, we're right now at like 1.226, which, you know, that's 1 millivolt, close enough for me. And our minimums right now are like 1.18 volts, but that's, or well, 1.19 volts, but that's without me moving the mouse. And if I move the mouse, we start hitting 1.13 volts. So we see about a 20 millivolt improvement compared to mode 1, which is actually kind of disappointing. You would think a 40 millivolt increase in V-droop would lead to a roughly 40 millivolt reduction in undershoot, but we're not even seeing that. So yeah, mode 5 is also just completely terrible. And the funny thing is, like, you might be wondering, wait, why would a 40 millivolt increase in undershoot, in V-droop, lead to a roughly 40 millivolt decrease in undershoot? And that's just sort of a thing that I've noticed with some motherboards. It's not universally true, and generally as your load line calibration gets more and more aggressive, the undershoot gets disproportionately worse. But yeah, so this is still unusable. We're averaging 1.226 volts, and we're seeing minimums as low as 1.1347. This is 1. Yeah, that's what, 90. So yeah, we've 90 millivolts of undershoot basically. Also bad. So yeah, you really got to wonder why MSI even bothered having a mode 2, 3, and 4 when mode 1 to 5 is not really an improvement. Anyway, now we're going to go to mode 6, which is actually going to start, cleaning things up a bit. So we're going to go to 1.3 volts and mode 6. I guess we could also try 1,000 kilohertz switching frequency at mode 7 or something. Actually, no, I don't want to try 1,000 kilohertz. The thing is, I've seen motherboards where the maximum switching frequencies are various levels of broken. Which is not good. Anyway, so obviously our idle minimum voltage is now way higher, right? We're all the way up at we're over 1.2 volts idle right now. But that's also because we're averaging a voltage of 1.28 volts. So that's really not surprising. If your average voltage is higher, your minimum voltage is also higher. So that's no surprise whatsoever. So, but once we run Y-Cruncher, I'm just going to reset the statistics. Our average voltage is around 1.228 volts, right? Which is very close to what we were getting at mode 5, which was 1.226. And our minimum voltage, if I don't move the mouse, is now 1.195, which is very close to that 1.228. That's within, 40, 30 millivolts, which is a very good result. Now, what happens if I move the mouse? Yes, it gets worse. Now we're seeing undershoot down into the 1.77 range, which is still, that's not that bad, right? That's what, 60-ish millivolts? 50? Actually, more like 50, isn't it? Is it yeah, it's 50 to 60 millivolts. So quite an improvement, right? We're no longer in that, mode 5 was hitting 1.13. We're now hitting 1.17. But I'm pretty sure we can do better. So we're going to go to mode 7 and then eventually mode 8. Yeah, I kind of wish MSI had actually having this many LLC modes. I think is actually kind of neat, but I would appreciate if there was if they had spaced them out more evenly. Though it would have made for a significantly longer video if they did that, because I'd have to actually show every single mode instead of just the ones that are worth. I mean, mode 5 isn't worth using. It's just kind of to demonstrate a point. Mode 5 is still bad. Anyway, now we're going up to 1.38 volts with mode 7. And mode 7 should actually be, relatively usable at this point. I think. I've not... the funny thing is, when I do the pre-testing for these videos, I only watch, only really pay attention to the average voltage and mostly ignore the minimums. So I'm actually not entirely certain how much better mode 7 is going to be compared to mode 6. Or... Like, I actually have no idea. But yeah, well, we'll see. Right? That's the point of this video. The average voltage is going to be still very close. It actually might be a little bit high. It seems that in pre-testing it was about 1.23 volts, which will be about 2 millivolts more than what we had for mode 7. But, you know, if your average voltage goes up 2 millivolts, but your voltage like your minimum voltage goes up by like 20, that's worth it, right? That's like a huge improvement in undershoot for a very small increase in average voltage. Anyway, so we're going to clear that. Obviously, idle is just like way higher because our average voltage is so high. Once we start the stress test, yeah, we get like 1.23 volts. The thing is, the voltage regulator on this board like goes in 5 millivolt steps, so I can't really do anything about this, right? If I reduce the voltage by another 5 millivolts, we'd be looking at 1.25 instead of, 1.225 instead of 1.23. Anyway, if I don't touch the mouse, everything looks very good. If I do touch the mouse, things look still pretty damn good. Yeah, like we're no longer seeing undershoot below 1.2 volts. We can still see that there's, you know, like compared to the sort of solid fat yellow line that we have right now, we can obviously see that if I move the mouse, there's some spikes downwards. But yeah, this is very solid voltage regulation at this point, and I think with a lower core count CPU like a 13600K, mode 7 would actually be extremely usable. Maybe even on a 13700K. Maybe if you ditch the E-cores, it would also be very, very usable. So yeah, mode 7 is actually pretty good. I don't really, like, it's not perfect. We can still see undershoot in the waveform, right? And I mean, if I'm not touching the mouse, we're seeing a minimum of like 1.215. And if I move the mouse, we see minimums of around 1.2. So we go from like 15 millivolts to like 30 millivolts of undershoot. That is a very solid result. Like, I think you could kind of make the argument for using mode 7 instead of mode 8. And this is the other reason, like, I really wish, like, imagine if mode 7 and 8, instead of having an 80 millivolt gap between them, had a 40 millivolt gap, right? And then there was, like, mode 6 was what mode 7 is right now. So, like, mode 7 would be, like, 1.42 volts, right? Which would get us very, very close to the voltage regulation that we're probably going to see with mode 8. And we'd have even less undershoot than we already have. Like, right now, mode 7 is... it's pretty good. It's not perfect, but it is pretty good. So yeah, like I wish MSI just like completely retuned the V-droop amounts. Like mode 8, what we're going to be using right now is going to be 1.46 volts. And so I really think it would have been better if like mode 7, instead of being like 1.38 volts to get 1.23 load, you know, it should have been like 1.42 instead of 1.38. And then mode 6 should have been the 1.38 that we use at mode 7. Mode 5 could have been 1.34. Mode 4 could have been 1.3. Mode 3 could have been like 1.26, 1.22. Well, yeah, I'd take 1.26, 1.22, 1.18. Right? I really think if these were actually like 40 even steps of 40 millivolts in terms of amount, like how much V-droop increases, I think that would have been a lot better than what we actually have here, which is 10 millivolt steps between the first 5 LLC settings, which makes basically 2, 3, and 4 completely useless. I mean, 5 is also completely useless from a voltage regulation perspective. Like, you know, like, yeah, no, like 5 is still terrible. So there's really, yeah. So it honestly, in a way, you could make the argument that this board has like 3 you basically have like 3 kind of usable LLC settings and then 5 that take up space in the BIOS. Anyway, so up to 1.46 volts we go. And mode 8. Let's see how this goes. And the thing with mode 8 on this board is, like, it is very droopy. Right? We have to go all the way. Like, it doesn't even fit on my oscilloscope's screen now. I have to pull it in. Which is not particular. Oh, I bet it's gonna go behind the... It's not gonna fit anymore. Oh well. Actually, no, it should fit. Yeah, it actually would have probably fit just fine, now that I think about it. But anyway, let's hit Y Cruncher. And, yeah, if we're not, so our average voltage is about 1.23 volts. It's actually a bit high again by another 1 millivolt. Maybe I should have punched in 1.455. Not that it would have, I don't think it would have drastically changed the results. Anyway, if I don't touch the mouse, we're seeing very similar results to mode 7 without touching the mouse, right? About 1.215, 1.212 volts right now. If I do touch the mouse... Huh. Okay, we see like a millivolt change in the minimums. Yeah, so mode 8 is very, very good. And this is the thing. If mode 7 was a little bit closer to mode 8... I think we could have seen very similar results from mode 7 already, right? If mode 7 was like 1.42 volts instead of 1.38 to achieve 1.23 volts average. And also, because mode 8 is so incredibly droopy, we're actually seeing the average voltage, like, you can see how our average is like 1.23 volts, but now it's come down to like 1.229. The reason that happens is because at mode 8, there is so much V-droop that as the CPU heats up and the average current draw increases, the voltage comes down because you get a little bit more V-droop. So yeah, this is such an aggressive, like such a large load line slope or such a steep load line slope that like small increases in current draw translate to noticeable increases in V-droop. So yeah, as the CPU gets warmer and warmer, you'll actually see the voltage come down a bit. Anyway, if we clear the statistics now, we see 1.229. If I move the wrong mouse, if I move the correct mouse, yeah, we see, what, like 20 millivolts of undershoot? Which is a very good result. So, yeah, also for some reason our average voltage has, like, gone up. Oh, and now it came back down again. Well, when I move the mouse around, like, you can see the mouse interrupting the workload, pulling the entire... Like, the big upward voltage spikes will obviously also affect the average voltage reading, so... Yeah, but we aren't seeing any more, like, difference between minimums without mouse movement and minimums with mouse movement. So, yeah, mode 8 is good. It's just, like, also not that... Like, you would need a lot of idle voltage, which I guess is why MSI introduced the Vcore suspension feature. So... Yeah, I guess I'll show how that behaves. It's a bit clunky. Man, and here I was like, oh yeah, this board only has like 5 LLC settings worth using. So this will be like a short video, and the video still ends up being half an hour. I don't know how I do this. And then I'm like, oh, we're also going to test this other feature at the halfway mark in the video. Anyway, so we're going to try the load line saturation control. Wait, did I say Vcore suspension? Isn't that like an ACES feature? Man, I get this stuff mixed up. There's too many of these. We're not going to try 100 amps, because I think at 100 amps it's actually going to not be that useful. We're going to do like 50 amps. I really wish I knew... Well, actually, so we've got like, what, 250... Off the top of my head, Y Cruncher with the settings we're running right now pulls like 250 amps. So if we're pulling like 250 amps, and we see we're going from like 1.46 down to, what is it? 1.23. We're seeing a 230 millivolts. So actually, yeah, that's about almost a millivolt per amp. Right, that's almost a millivolt per amp. So if I enable a 50 amp load line saturation, then logically we should have to reduce the idle voltage by about 50 millivolts. So we're going to go down to I'm actually going to be a little on the safe side, Because basically what this does is it reduces, like, it basically moves the starting point of the load line. So from 0 to 50 amps, we're going to have 0 V-droop. And then past 50 amps, we get the full mode 8 amount of V-droop, but offset by like 50 amps. So, yeah, so like 1.4 volts should be about right, I think. I might be a bit low. Well, we'll see. If I'm a bit low, we can add 10 millivolts or subtract 10 millivolts. And I guess the idea from MSI on this is that you can still use a very droopy LLC like level 8, but you're not going to have the, like, you're not going to have the insanely high idle voltage that you would potentially need. Yeah, so, like, a decent idea. Obviously, if you put more time into tuning this, I think you could get better results. And this is really interesting, because at idle, we're actually... Like, we're not really seeing the effect of the... Did it not kick in? I guess the invent timer actually manages to pull 50 amps. That's interesting. Okay, let's hit Y cruncher. Hey, I wasn't that far off. Yeah, so I was a little low. Evidently, I should have punched in 1.42 instead of 1.4, because we're getting an average voltage of 1.2 volts instead of the 1.2. Actually, should have punched in 1.43 volts, because yeah, we're 30 millivolts below what I was aiming for. But if I move the mouse, yeah, we don't really see a significant increase in undershoot. So yeah, this is actually a really pretty helpful feature. We're just going to restart. Like, it's a pretty easy way to, like, save yourself a bit of idle voltage without really negatively affecting the voltage regulation whatsoever. And obviously, you could increase the saturation current to, like, further reduce the idle voltage. I really wonder how this is implemented. Because it kind of, like, in a way, you could sort of think of it as like a negative load line offset. Anyway, so maybe we'll go up to, like, say... Let's go up to, say, 75. And if I... Yeah, and if I'm not mistaken... Actually, let's go up to 70. And I think... At this point, 1.4 volts should get us pretty close to the 1.23 volts under load. Unless I got the... Unless I'm thinking of it backwards, which is very possible. Anyway, let's start Y cruncher again, and yeah, we get a bit more load voltage. Yeah, we're now at 1.21. So actually, I could have given it even more. So yeah, pretty interesting feature that MSI has here. Like, it basically means you can use mode 8 LLC and just kind of use the load line saturation to tune out most of the, like, excessive idle V-droop. Still doesn't justify having 5 redundant LLC settings, but this is a pretty neat feature. Yeah, so I guess that's gonna be, like, if you have this board or other boards from MSI that have this feature, I guess the way to go, like, to go about overclocking with them would be to use mode 8 LLC, and then just fiddle with the saturation current, to get desired behavior. I'm kind of wondering what'll happen if we set it to like 100 amps. Because I think there's a point where if you like keep increasing the saturation current, like at some point it's actually gonna... Like there's got to be a downside. Like you can't just punch in like 200 amp saturation current and set your like idle voltage to the same voltage as your load voltage. I'm thinking like there's got to be some workloads at that point which will like not get good voltage regulation anymore if you do it that way. I'm gonna set this to like, we're gonna try like 120 because when I first tried this feature, I tried it with like 100 amps and it didn't seem that useful when I did that. So we're gonna drop down to I think 1. Like the thing is we're on a 280 millimeter AIO right now, so I don't really have unlimited cooling potential, so I don't really want to shove a way more voltage into the CPU than necessary. Because well, actually, like 1.2... Oh, yeah, now we're starting to see it. Yeah, because now we're going to start seeing, like, idle... Yeah, you can start seeing that there's, like, upwards voltage spikes at idle now. Because basically what the load line saturation setting does is it... like, when you're below the saturation point, you have no V-droop. So... below 120 amps, we're basically on like mode 1 LLC. Now, the thing is, if at idle we're still getting perfectly acceptable minimum voltages, right? Because like the idea with the load line is like, well, if I run Y-Cruncher and my minimum voltage when running a Y-Cruncher is 1.2 whatever volts, then as long as my voltage never goes below 1.2 whatever, in any other scenario, then actually I'm okay in terms of stability. Right? Because if I'm playing a game and my minimums are like 1.25 volts, it ain't gonna crash, right? Because if Y-Cruncher doesn't crash at 1.2 whatever volts, then 1.25 during gameplay or something is also going to be completely safe in terms of stability. So, yeah, now if we hit Y-Cruncher, click on it, I think we saw something a bit... So now we're getting 1.21, and of course voltage regulation is good. I think there was something a bit... I'm going to zoom out more, and we're going to do single. I'm just going to start Y-Cruncher. Okay, no, the transition is very clean. So the one concern I had is like, well, what if in the transition point you had like massive undershoot, right? But we're not seeing that. Like that is a very, very clean transition right there. And once Y-Cruncher is running, everything's good. And before Y-Cruncher runs, I go for a single again. Oh, it... There, yeah. So that looks good. Cool feature. Very cool feature. And you can evidently be quite heavy-handed with it. Like, I didn't think 120 amps would, like, still behave well. Right? I guess we could maybe try something a bit different, like, say, a Cinebench. But the thing is, Cinebench should be well above the voltage requirement. I guess the other option is also, like, a very transient... Because the thing is, the way I have Y-Cruncher configured right now is it's a very static current draw. Run Cinebench, and I'm going to zoom us back out. Yeah, so once Cinebench is up and running, everything is good. Unsurprisingly, because we're past the saturation point. So what we're going to try next is the Y-Cruncher Pi benchmark, which is very inconsistent in terms of power consumption. This is one of the noisiest workloads that I'm aware of. question is, are we going to see something... It dips all the way down to 1.2. I mean, there was also a 1.19 on there, but we can just run it again for that. It looks a lot worse on Ryzen CPUs. Like, this is, or, well, actually, no, I might be thinking of something else. I also have the trigger in there, which we don't really need. We're going to pull the trigger out. Anyway, we're going to hit that again. I'm going to reset the statistics. Okay, so there's an initial, like, 1.198. Kind of wonder what would happen if you, like, hit this over and over and over again, like, in rapid succession. But I don't think it's going to be... I don't think it's worse than just Y-Cruncher with the mouse movement. The small FFT test. Also, this video is probably going to end up being an hour at this rate. Yeah, well, that looks good. Yeah, so now what I want to check is, well, okay, what does Y-Cruncher look like when you run small FFTs? Can we move the mouse? Yeah, this is actually still worse, right? Like, we're getting that, now we're getting, like, even lower minimums. We're getting, like, 1.1925. And if I go back and quickly run Y-Cruncher Pi, the minimums don't get any worse, right? So this is a very dynamic load with a very inconsistent current draw compared to small FFTs, and it's actually not hitting lower minimums. So that's a very good result. Oh, so it works great. Really, really neat feature from MSI. I guess I kind of It's funny, because starting out this video, I thought it was kind of useless. Because in my initial tests, like, I sort of saw that at idle it wasn't doing so great, but I was testing it with, like, mode 6 LLC instead of mode 8, which probably wasn't helping. Because mode 6 isn't, like, we've already seen, like, mode 6 doesn't get you anywhere near perfect voltage regulation, right? Like, mode 7 or 8 is, and actually, if you're using the saturation thing, like, use mode 8. Like, the only reason you wouldn't use mode 8 is that your idle voltage goes through the roof, but, like, with this, you can basically shift your idle voltage down, and, well, I guess the one concern with this is, like, I'm kind of wondering is, like, is there a scenario where... Because the saturation current, I would imagine it's relatively specific how high you can set it for each CPU. Like, at 120 amps for, like, a 13600K with, say, the E-cores disabled, well, the 13600K maxes out at, like, a little over, I think, 150 amps in terms of current draw. So this configuration that I'm testing right here would probably not actually work very well on a 13600K. So... it's a bit CPU specific, and obviously without an oscilloscope, it's going to be very difficult to see if you've, like, set your saturation current too high, or, like, load line saturation too high. But I guess there might be some way to test. And I guess you could also probably calculate some, like, basic rule of thumb. Then again, if you're on a 13600K or something, right, like, the CPU pulls so little current to begin with that your idle to load voltage difference is going to be relatively small to anyway. Right, like, that's the other thing you have to consider is, like, well, if your CPU goes from pulling 10 amps idle to 250 amps load, then yeah, you're going to see a really big big V-droop on mode 8 LLC. But if your CPU goes from pulling 100 amps to 150 amps, you're going to see like 100 millivolts less V-droop than a 13900K does. And so a feature like the load line saturation becomes somewhat less useful because there's just a much smaller gap between your idle and your load voltage. But still, this is a very, very cool feature that MSI has on I'm not sure if they have it on all of their boards, but they certainly have it on this board, and I imagine higher end boards than this one would also have it, and any boards that use the similar VRM configuration, I would assume also have it. So yeah, a pretty cool feature, and you know, I guess I can forgive the completely redundant LLC settings going from like 2, 3, 4 definitely are completely unnecessary in the BIOS. I really don't see any purpose in having those. Like, there's some argument to be made for having an LLC setting with no V-droop, because if you're doing like thermal testing or something, you don't want your voltage moving around. Okay, like there are like scientific applications for not having V-droop. There are no like real world practical applications for not having V-droop. If you want to like test heat sinks or water blocks or something, you don't want your voltage moving around based on V-droop, right? Like, you don't want that. That would totally throw off your results. If you're trying to test the power delivery capabilities of the VRM, you don't want the average voltage moving around. But if you're actually like trying to get the best overclock out of your CPU, well, you don't want terrible voltage regulation. So, like, there is a good reason for boards to have a 0 V-droop LLC. But then, like, mode 2, 3, 4, where it's like, this is almost 0 V-droop, but not really 0 V-droop, is like, why does this exist? The voltage regulation sucks, and you wouldn't use it for, like, thermal testing or anything, so it's just kind of there. Anyway, yeah, that's it for this video. And I guess thanks for watching. Like, share, subscribe, leave any comments, questions, suggestions down in the comment section below. If you'd like to support what I do here with actually hardcore overclocking, I have a Patreon. There's a link to that down in the description below. There's also the AHOC Teespring store where you can pick up shirts, hoodies, posters, you know, the usual YouTuber merch. And I've also got a Bandcamp. There's a link to that down in the description below as well. And that's it for the video. So thank you for watching, and goodbye.